All right, so you should have your notes out. I believe they look like this. Am I right? Does that look right? Okay. So we talked about ionic bonding in the last chapter. Now we're going to talk about covalent. So non-metal, typically anything that is a metal and a metal is metallic bonding. Anything that's a metal and a non-metal is ionic, which we've already covered, and we have to transfer those electrons and keep track of all the charges and all that good stuff. Here, we don't have to keep track of the charges, but because there are no charges, but here they end up sharing electrons, and that's called covalent. Okay? So a covalent bond, oops, back up. I don't like this. I don't like that 2. That 2 should be a subscript. Control C, V. Deal with that, and don't make me look at it to see it. Okay, Control dash C, Control V. All right, that's better. Save. All right, make that bigger so we can talk. Okay, so when these covalent bonds form, they're going to share the valence electrons. A molecule is what we're going to create here. Okay, this is formed when 2 or more atoms bond covalently. We do have diatomic molecules, and we've touched on those a little bit back when we were talking about elements, compounds, and mixtures, and how we end up having different things form, and we kind of looked at a particle view of that. Now we're just going to talk about it in terms of what they are. So we're going to identify them. And we refer them collectively as Brinkel-Hoffs. So if you say Brinkel-Hoff, that tells you the elements that are diatomic, meaning that when they're found in nature, they're always, it's a pure sample, they're always bonded to another one of their element. Okay? So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. When we write them, they get written like this. So this was number 7 on your quiz last week, where I said, oh, I forgot to tell you about these. You don't know how to write them as formulas. So if you do a retake now and you see any of these and it's just that lone atom, like just one thing, that this is what you're going to write down, and I'm not giving you any freebies on those quizzes anymore. So, okay. And these are going to come into play when we start writing formulas. And you've seen like oxygen when it's been written like this, like with cellular respiration or photosynthesis, you've always seen that oxygen is O2. That's why, because it's always bonded to another oxygen. All right, we have sigma bonds done. Sigma bonds are single covalent bonds. Our orbitals are going to overlap end to end. And it's going to concentrate these electrons in a bonding orbital between 2 atoms. So sigma bonds are end to end. They can form in a couple of different ways. We can have the s orbitals overlapping side to side. We could have an s and a p overlap side to side. Or we could have 2 p orbitals overlap side to side. These are called sigma bonds, and these are always your single bonds. When we have a single bond, you've heard of single, double, and triple bonds before, probably. Okay, these are always your single bonds. Remember, single bond and sigma go together. Okay, same letter. All right. When we have multiple bonds with atoms, sometimes we have a double or a triple bond. They share more than one pair of electrons with one atom, common in your carbon, oxygen, nitrogen, and sulfur. The number of valence electrons then is needed to form an octet equals the number of covalent bonds formed. So when we have double bonds, we're going to have a sigma bond, and then we're also going to have a pi bond. So we have a sigma bond for one pair, and then the other pair is going to be a pi. This is where the p orbitals, and it's always the p orbitals, they're going to overlap side to side. So before, with a sigma bond, they overlapped this way. Here, they're going to overlap this way. A sigma bond is stronger than a pi bond. A triple bond then is going to be 3 pairs of electrons where you have 1 sigma and 2 pi. I feel like I'm talking about a recipe. 1 sigma, 2 pi. Oh, these subscripts did not follow through on here. I'm sorry, guys. Hydrogen, 1 pair of electrons are shared. Group 17 needs an electron, so that would be like your F2. Group 16 would be like H2O. Group 15 would be NH3, and group 14 would be like CH4. Okay? Oh, okay. Now we're going to switch over. I don't like the notes that I gave out to you originally, so we're going to switch over to a different set, and I've got some other stuff to hand out to you. So here we go. And this I'm going to leave here because I got to draw on these slides. All right, let me hand these out to you guys. All right, so Lewis structures. We have talked about Lewis dot structures before. I taught you how to write those in chapter 5. Okay, remember how we figure out how many electrons or how many valence electrons we have. All we have to do is count on our periodic table. 1, 2, skip a few. Not that we need to mess with those. Why don't we need to worry about our first 2 columns for covalent bonding? Covalent bonding goes between what? Yep. Right. So those are all metals, so we don't need to mess with that. But we go 1, 2, skip a few, 3, 4, 5, 6, 7. So that 3 through 7 is what we're going to care about. Okay. So you got to be able to do that, count those. So when we do the Lewis dot structures, let's say what we've got sulfur. Sulfur would be 6. So sulfur would look something like this. Okay. When atoms form molecules, they're going to share electrons to fill that S and P orbital level. In the case of hydrogen, it's going to be satisfied with 2. So it comes with 1. Remember, hydrogen needs 2 to be filled. In the second period, metals, nonmetals, this is the 8. And further down, some elements in the third period can have more than 8 electrons, which is called an expanded octet, because some of them have empty d sublevels, which is available and make it available for bonding. So sulfur is an example of that. It can actually have more than 8. It can expand its octet. All right, so fun times. We are going to we're going to calculate the total number of valence shells available, adding in negative charges and subtracting for positive. So for example, if you had NH4 plus, okay, this would have how many electrons? What column is it in? 5. And this would have 4, so that's 9, but this is a plus sign, so it actually only has 8 electrons. If we had like SO4 minus 2, okay, Here, you would have 6, and then 6 times 4 is 24, plus the 6 is 30. But we have a minus 2, so I need to add in 2 more electrons. This would have 32 electrons. Okay, so that's what they're talking about subtracting or adding in. Then you're going to arrange the, so you're going to, in the species with more than 2 atoms, you're going to decide which one's the central. So the central one is going to be the least electronegative. The nice thing about that is typically the least electronegative is always listed first in the formula. So if you did this, for example, your hydrogen would be your least electronegative. Now there's a problem because hydrogen's always on the end, so that's not a great one to show. Let me see if I can think of another one off the top of my head. Here, CH4. Okay, your carbon's going to be in the center. This is your formula. It's typically the element that's in the front that's going to be in the center because that's the least electronegative. The terminal or outside elements are bonded then to that central atom, and you have to arrange the remaining electrons to form octets, or in the case of hydrogen, a duet. If the central atom then lacks an octet, you have to form multiple bonds to be able to get that to happen. And one bonding pair of electrons we represent with a line that's going to equal 2 electrons. Any electron pairs that occur in the valence shell of an atom but do not form a bond are called non-bonding electrons or lone pairs. And these are going to become vitally important to us in the end of this week. Okay. So here is our phosphorus. We're going to count up how many PCl3, how many electrons we have. So phosphorus has 5. This has 7 times 3 is 21, giving us a total of 26 electrons. So you go through and you add in your central atom. Again, it's typically the one listed in the front. And then you add the other ones around it. So once we have that surrounded, then we go and we place our electrons around. So 2, 4, 6. This line is how many electrons? 2. So 2, 4, 6, 8. So the octet's satisfied there. Here, same. Here, same. Now, how many electrons do I have placed? 8 times 3 is 24. I've got 2 more left over, and phosphorus needs extra electrons. So I'm going to put those here. These are called lone pairs of electrons. And again, these are going to become vitally important to you later this week. All right. Some atoms remain electron deficient, meaning that they don't need a stable octet. Boron tends to be the only one that really happens with, and the only one that you need to think about. But boron's actually happy with 6 electrons. Everything else pretty much needs 8, unless it's hydrogen. Okay. We also have these things called expanded octets. So your sulfur, phosphorus, chlorine, bromine, selenium, arsenic, tellurium, iodine, astatine, they can form these expanded octets because they have a d orbital that's open to be able to form that. I think this is the last thing that we get into. Yeah. So the last one is coordinate covalent bonds, and we'll get into those more when we move through this. But you can have certain elements or certain atoms can contribute both the electrons to a bond. Okay. And a lot of this is going to come with you practicing drawing these. You'll get used to how these work. When you do have one of those charged particles like the NH4 here, that you need to make sure that you put the drawing in brackets and put the charge outside. The last thing that we're going to talk about is resonance. Resonance then is where you have a structure that you can draw. Let me see if I can make this one bigger so you can actually see it a little bit better. There we go. So when you draw this structure, it has this double bond. That double bond could be here when you draw it. It could be here or it could be here. And so if they ask you to draw all possible resonance structures, you'd have to draw all 3 of these. And it also takes these lone pairs of electrons and kind of flips them to wherever that double bond is. There we go. Oh, things that you need to remember. Each atom has to get an octet except hydrogen and boron. Nonmetals in period 3 and onward can expand their octet. Hydrogen and fluorine are always terminal, meaning that they're always on the end. They can't be the central atom. Each electron pair equals a bond, and pairs of electrons in the valence shell not bonded then are called lone pairs. All right, so let's get started with the fun. All right, so I do this in a lot of different colors here, guys. So I'm going to, first of all, carbon is listed first, yes? Then that's going to be my central atom. Okay, I'm going to draw in, and make sure you're using pencil for this. Don't use pen for this. You're going to be erasing a lot. Okay, so I've got my carbon drawn in. How did I know that it has 4 electrons around it? It's in the 4th column. All right, now I'm going to draw my hydrogens in. My hydrogens, I'm going to draw in one here. I'm going to draw in one here. I'm going to draw in one here. And lastly, one here. Okay, so now I'm going to go back. I'm going to make sure that everything is filled. So here I've got this. Hydrogen needs 2 electrons. It has 2, has 2, has 2, has 2. Carbon needs how many? Carbon needs how many to be satisfied? 8. It needs an octet. It has 4 to give, okay, but it needs 8. And each one of these hydrogens is giving it the one it needs. So that gives carbon its 8. Typically, you'll see this drawn like this without the dots. Okay, each one of these lines represents 2 electrons. So 2, 4, 6, 8, and then your hydrogen is 2. All right, questions on that one? All right, fluorine has how many? 7. So I'm going to draw my 7 for one fluorine. And then I'm going to draw my other fluorine in. Okay. Now this fluorine, by sharing, it has 8 electrons. And this one has 8. So everything's good. All right. Next one is oxygen. How many does it need? It needs 2. It has 6. Okay. I got my one oxygen drawn in there. I'm going to draw my other oxygen in here. All right. Oops, I drew too many. There we go. All right. So now, if I look at this, how many does this oxygen have? 7. It needs 8. Okay, there's a problem there. I'm going to take these 2 away, and I'm going to draw them back in with a bond. Okay. And I'm going to kind of color code my bond just so you can kind of see what's going on there. So 1 electron's coming from here, and 1's coming from here. All right. So now what I need to do is I need to take this electron, because I need 8, and I can't add any more electrons. I've got all my electrons placed that I had. So what I'm going to do is I'm going to move this electron into the middle, and I'm going to move this electron into the middle. And by doing that, watch what happens. Huh? Yep, it's called a double bond, right? Okay. So now this oxygen has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. Make sense? All right, let's look at this nitrogen. Nitrogen has how many? 5. 1, 2, 3, 4, 5 from my other nitrogen. Oops, I drew too many. Okay, so this one right now has 6 electrons. This one has 6. We need 8. Can you figure out what we got to do? Yep. We're going to do the same thing we did as with oxygen. So I'm going to move that one. I'm going to move these 2 in and make them a bond. So I move those 2 in. Now what do I do? That's the same as oxygen right there. What do I got to do next?
One more bond to virtual bond.
How do I do that? Yep. So I'm going to take this guy away and this guy away and bring that into the center. So now I've got a triple bond. So this nitrogen has 2, 4, 6, 8, and this nitrogen has 2, 4, 6, 8. All right, the next one is HCl. So I'm going to draw my H in. It has 1 electron. I'm going to draw my chlorine in. It has 7. All right, now my hydrogen has 2, which is all hydrogen needs, and chlorine has 8. So see if you can draw HF yourself. Got my chocolate covered cherries made last night, guys.
Ooh.
Got my fudge made for you guys. My caramel. Got it in the next couple days for your Christmas treat. If you've never had homemade caramel, it is melt in your mouth, like literally melt in your mouth. You don't have to chew it. It's not the Brock's cheap caramel that you buy at the store, you know. This is a Christmas treat, trust me. Not bragging on myself, but I love my caramels. I make them one time a year because if I made them any other, I just go through the whole thing. All right, y'all figure this one out. It's pretty much the same as this, right? Except we had fluorine here, right? So it should look like that. I'm going to be lazy and just do that. Okay, good. All right, let's look at the next group here. Huh? Well, you should be able to figure out should be able to do. Yeah, I think. Why don't you guys try to do this one, this one, this one, and this one? Those should be easy. And then we'll come back. We'll do the last 2 together, okay? Let's see if you can do those first 2. 4. I'll give you guys just a minute to do that. I'm going to see if she's still up front there.
Nitrogen.
I hope she makes this harder.
Yeah, because then it gets interesting.
Yeah, but don't you need your grade to get up in here?
Ben!
Why?
I would rather have some sort of content that I can actually grasp because I've been doing better this year. Just say I'm starting a fight.
I said 5 fluorine. I don't like to read that.
Oh,
Then you can.
that's scary.
It's phosphorus will get.
I usually buy coffee.
Right. Okay, number 10. That, oh, are these not in the same order as mine?
No. Wait.
Oh, yeah, they are. Yeah. Oh, this one's an expanded octet. I don't know that you'll be able to do that one. So just do the first 3, I guess. The first column. Sorry.
Nice shot, Brendan.
All right, so the first one here, you had H2O. You should have had your oxygen. You have your 6 electrons around your oxygen. And then you're going to come in with your hydrogen here and draw your hydrogen in. Good? All right, nitrogen has 5. And then your hydrogen's going to come in and it's going to donate. This is kind of like a jigsaw puzzle almost. Okay, trying to figure out how to get the pieces to fit. And then your carbon is going to be here with the bromine around it. This was kind of a frustrating one to draw because you've got so many electrons around bromine. Squeeze him in down there. There you go. Okay.
Missing 2 on the bottom bromine.
Oh, yeah. There. Better?
Yeah.
Okay. All right. Everything's happy. You're happy. Life is good. All right. This guy then, we've got our phosphorus in the middle. Fluorine always has to be on the outside. Always. No questions asked. No. Huh?
Unless it's very high.
Well, you could, it wouldn't be on, it would still be on the outside because you could only do 1 on each. So that's all you can do. Because this can only have an extra one and this can only take 1. So it has to, yeah, it's still on an end. It's just nothing's in the middle. Sorry. All right, so I'm going to put my fluorines around here. And this is one of those expanded octets because remember phosphorus is in the 3rd period. So it can expand its octet and give room for these fluorines to get in there. So once I do this, then I've got all of my electrons placed and life is good. And you should always kind of double check your counts when you're done to make sure that you didn't put too many in there. So my phosphorus had 5. This had 7 times 5 is 35. That means that I should have 40 electrons around this. Right? Am I missing 2? Okay. So if we're missing 2, those have to go on the phosphorus and they're going to be lone pairs. Okay? So 1, 2, 3, 4, 5. 5 times 8 is 40. So I needed to have 40 and I've got 40. So I'm not missing 2.
We have 5 around 2 and 40. Oh, the bottom one. The bottom one, yeah, you looked right at it.
Good? Okay. But I've got 40 now, right? So I'm good? All right. So this is PCl6. So this is going to have 7 times 6 is 42 plus 5 is 47. But do you see this guy right here? So that means that we've added in an electron. So this is actually going to be 48 electrons. So see if you can draw this one in. And then I'll show you how to do charge with it. You know it's going to be an expanded octet. So see what you got to do with that.
Is this as hard as this part's going to get? Or is it
I think it's a little worse. All right, looking good. So then make sure you've got all 48 placed, do you? Did I do it right, Ben? All right. The next one then is my nitrogen. So my nitrogen has 5 electrons. So 1, 2, 3, 4, 5. And I've got 4 hydrogens to place around here. So I need to place my hydrogens around. So 1 goes here, and 1 goes here, and 1 goes here. But that doesn't leave me a spot for my other hydrogens. Oh, I forgot on this other one. Sorry. We'll go back and fix that one in a minute. But this says a +1. So what does that mean has happened? We lost an electron. So this electron is gone, which leads us to be able to put our other hydrogen in here. Now, when these are charged, you should have square brackets around them to indicate that they're charged, and then you put the charge outside that square bracket. And that's what I forgot to do up here on this guy. So he should have had a bracket. And on the outside of that, I should have had a minus sign. Sorry about that. All right. So you've got homework. We're going to go over a couple of your homework problems first, because I think I need to talk to you about a CC bond. If I'm not mistaken. Where is your packet? Could it be? Where is your packet? For me.
Actually, on one, getting the 6 through the floor. Getting the 6 through the floor.
You're talking about the.
Okay. So CO2, number 9. I want to do number 9 together.
It just made everything stable. So if it were not charged, it would. If it weren't charged, you just like everything.
All right, I want to do CO3 with a -2 charge with you. Okay, this is number 9 on your homework. So we're going to do that one together. So what's my central atom? Carbon, because that's the central one. So that's going to go in the center here. My oxygens then are going to go around that. So I've got my carbon drawn in here. And now I'm going to draw in my oxygens. Okay. And I'm going to draw in all my electrons for my oxygens. Oops, I put too many in there. There we go. All right. I hope you're doing this in pencil. All right. So I have to be able to get this up to 8. Right now, this carbon is only at 7. Okay. So what I'm going to do is I'm going to take these 2 electrons away, and I'm just going to represent them with a bond. Okay. So I'm going to do that in black. That is my 2 electrons that were here. Okay. Now I'm going to bring in this electron, and I'm going to bring in this electron. Okay. Everybody cool with that? Okay. I'm going to bring those in, and I'm going to form a double bond here. Try anyway. There we go. No, well, look at these 2 here. See that? I've got a problem. So what I'm going to do is I'm going to shift. I'm going to take this. Okay, what do I do here? What do I do? Oh, I've got 2 extra electrons. That's what it is. Okay. So I've got 2 extra electrons here. So I'm going to bring in these 2 electrons here. Oops. I'm going to bring those in. So if I put one here and I put one here, that's going to give me my full octet. So now this has 2, 4, 6, 8. This has 2, 4, 6, 8. This has 2, 4, 6, 8. And so does this one. Now there's one more thing that I need to do to this drawing to make it right. What do I need to do? Yep. I need to put those square brackets in and put my -2 charge here. Okay. Now, all of the answers are out on the internet. So if you want to check your work as you're going through these, all you have to do is go to Google Images, type in this formula, and I can guarantee you're going to get a Lewis dot structure coming up for you. If you don't, then type in the formula and say Lewis dot, and it'll come up. I'd put money on it. All right, and that still didn't have a coordinate covalent bond in it, despite what the key said. I guess we'll get to those tomorrow. All right, so you got time to work on these. You got about 10 minutes. Yeah, just sign out and take a pass, please.